Assalamu alaikum. I am Abdul Malik Marwan, and this is video for the foundation design project. And we are from group 2. Our lecture name Dr. Kamaluddin Ahmed. Our company Geotec SDN. So the rating structure for our company Muhammad Arshad. The shallow foundation design Asif and Kabir. And the bio foundation Sajid and Omar Abdul Sattar. And the programming me, Abdul Malik Marwan. Geotec SDN was invited to submit a design proposal for proposed interchange bridge. This report includes all the results of geotechnical asset investigation, retaining structure, shallow foundation, and pile foundation for the proposed interchange bridge project. So as we can see, this soil profile diagram for borehole 3 and borehole 5, which is located at the proposed site of the construction of interchange bridge. So the perform the calculation of the retaining wall and the shallow foundation and pile foundation.
Assalamu alaikum, I'm Mohammad Arshad and I'm in charge of retaining wall or bridge abutment. So in simple terms, retaining wall is a substructure that's placed at the end of the bridge that holds the soil and supports the superstructure or the bridge, and it prevents it from overturning, sliding or settlement while transferring the surcharge from bridge to the ground. So in this project, we decided to choose cantilever retaining wall over the others because it's very common and economical, as less concrete is required compared to other types. Now moving on to the design parameters, we have considered silty sand layer as the backfill soil with a negligible cohesion value, and here are the assumed values and soil characteristics for different layers that will be taken in account during the analysis. The layers are determined based on borehole log 5. So first and foremost, the active soil pressure acting on the structure due to the surcharge acting on the backfill was calculated. So after determining the coefficient of active pressure using the following formula, the highest value for active pressure is found out to be 54.01 kilonewton per meter square, and it acts at the depth of 9.5 meter from the top. After this, we calculated the dead load of each section of the retaining wall and determined the perpendicular distance from the centroid to the overturning point in order to estimate the moment. Then using the total moment due to the structure and active pressure, we found out that the resisting moment was 3.73 times higher than the overturning moment, hence the structure is safe from overturning. Then for the stability check against sliding, we compared the factored horizontal load with the factored vertical load by multiplying with the friction coefficient, and found out that the friction force is 1.4 times higher than the sliding force. So therefore the structure is also safe from sliding. Lastly, we checked the settlement due to eccentric load acting on the structure and calculated max bearing capacity of the soil using Meyerhoff's formula, and found out that the contact pressure due to load is equal to 159.12 kilonewton per meter square, which is much lower than the max bearing capacity, which is equal to 1753.14 kilonewton per meter square. Hence, we can conclude that this design cantilever retaining wall is safe from all kinds of failure.
I am Asif. As you can see on the screen, for this presentation, my part is shallow foundation. So let's start with the basics. What is shallow foundation? So shallow foundation is when the depth of foundation is equal or less than the width of foundation. We consider it as shallow foundation. So based on the briefing of project, we can extract the following data. That is, height of clearance of foundation of column is 6 meter. Depth of footing must be less than or equal to 3 meter. So we have assumed it as 3 meter, and we assume that it is a square footing. So or B equals to L, and we assume it as 4 meter. And for thickness of footing is 0.5 meter. We assume factor of safety as 2.5, and vertical load is given, that is 10,000 kilonewton, and also the horizontal load is given, that is 800 kilonewton. Here is the drawing of our foundation, and in the drawing you can see that the depth of groundwater table is 1.5 meter from the ground surface. As we know that for the design of shallow foundation, we have to follow Meyerhoff design process. Here are the content of this process. So the first step is to determine the eccentricity. So the horizontal load, that is 800 kilonewton, acting on the right side of footing, which produce the movement in the B direction. After using the equations, we can calculate the value of eccentricity, that is 0.486, which is less than B over 6. So it is okay. Our second step is to determine the effective depth. After calculating the effective depth, we will use the Meyerhof equation to calculate the ultimate bearing capacity. After that, we have to check maximum and minimum stress cases. Based on the data, our Qmax equals to 1598 kN per meter square and Qmin equals to 250 kN per meter square, which is greater than 0, so it is applicable. After that, we have to calculate our design factor, which is equals to bearing capacity over vertical compressive load. So our design factor is 1.1, which is greater than 1, so it is also applicable. In the end, we have to calculate settlements. There are two kinds of settlements underneath foundation, that is elastic settlements and consolidation settlement. Our settlement value is 262 mm, which is greater than 50 mm. So in the end, we can conclude that the design of our foundation is insufficient because the settlement value exceeds the maximum limit of settlement. Thank you so much.
Assalamualaikum everyone, I am Kabir Alamgir. Now I am going to talk about the shallow foundation combination 2 using the Meyerhof equation. As our group member Asif already mentioned it before, that we have to use this data to calculate our combination. So this is the Meyerhof design process. We have to follow this step to calculate the combination 2. So at first we have to determine the eccentricity. That we got the eccentricity value is 0.657, and that is less than B divided 6 value. The B divided 6 value is 0.67. Then after that we have to determine the effective depth. That effective depth calculation. After that we have to do the design resistance. Then after that we have to calculate the shape factor. After calculating the shape factor, we have to calculate the inclination factor using horizontal load and vertical load. After calculating all the factor, we have to calculate the bearing resistance using Meyerhof equation. So we have to put all the factor in Meyerhof equation, then we will get the bearing resistance. So for bearing resistance, we got 1746.5 kilonewton per meter square. So after calculating the bearing resistance, we have to check the maximum and minimum stresses. So for the maximum stresses, we got 1359.17, and for minimum we got 9.93, that is greater than 0, so it is okay. So after that we have to calculate the over design factor, that we got 0.67, so it is not okay. So at the end we have to calculate the settlement. So for settlement we got the value is 191 millimeter. So we can say it is the most critical one. So at the end we can see and we can say that the design is sufficient, since the total settlement extend the maximum settlements. Thank you so much.
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Sajid Alam and I will be presenting the pile foundation. What is a pile foundation? The pile foundation is one sort of deep foundation. The pile foundation supports the structure and distribute weight at a set depth using frictional or shaft resistance force or in-bearing forces. The large structures frequently require pile foundations as to situations where the shallow depth soil is insufficient to withstand the lateral loads, uplift and other problems. Thus, to create a solid foundation for structures that are built on top of them, piles are driven into the ground. As structures are built on top of them to transfer the weights from the buildings to hard strata, rocks or soil with a high carrying capacity, piles are utilized. In our instance, borehole log 5 is being used to create pile foundations. When there is brittle soil, pile foundations are typically built. By using piling foundation, the loads can be transferred from a layer of brittle soil to one of sturdier soil or rock. Thus, we use borehole log 5. Now let's look at the design data. It was given already the vertical compressive load, the longitudinal horizontal traction force, and the live load due to the traffic. Then we assume the unit weight of concrete as 24 kilonewton per meter cube, and then diameter of pile we assumed as 1.5 meters, and then the perimeter of pile we calculated as 4.71 meters, and the area of pile we got 1.77 meters square, and then the length of pile, that is 20D, we calculated and got 30 meters, and then area of contact between pile and soil we got 141.3 meters square, and then we take the factor of safety as 2.5. Assumptions. The first thing we assume is that the vertical load acts on the center of pile cap. Number 2, the uplift is 50% of the calculated friction. Number 3, the design pile is assumed to be high displacement pile. And number 4, the pile undergoes both in-bearing and skin friction. The formulas. Let's look at the formulas that we used. The formula that we use for the calculating pile capacity at this one, we use separate formula for silt and sand layers, and then the formula that we use for the allowable ultimate pile capacity is this one, and then the formula that we use for uplift capacity is this one. The design data and using the SPTN approach, the maximum pile capacity QU is determined. Then for this hypothetical interchange bridge project, both a single pile foundation and a group pile foundation have been constructed. So in our calculation part, we take into account our depth of each layer and also the SPTN number of each layer, and then we take the average, and then we calculated part by part all the pile capacity and the allowable pile capacity, and then the uplift capacity and the allowable uplift capacity from the tabular method. And then in the end, as a result, we got that the allowable pile capacity is 15,351.62 kilonewton, which is greater than the applied one, and the allowable uplift capacity is 2,113.39 kilonewton, which is greater than the applied one. Thus, we can conclude that the design of single pile foundation can cater the loading applied. Thank you very much.
Hello, my name is Omar Abdusattar. I am in charge of designing the group pile foundation for the proposed structure. First, we will be calculating the maximum design load that can be carried by the foundation, and then we will look into the eccentricity caused by the horizontal load. So let us proceed. First, we make a table using the data obtained from the borehole log. We split the table whenever the soil type undergoes a change. For example, from loose silty sand to firm sandy silt. For each type of soil, we calculate the average SPTN number, and then we calculate the QS, which is the shaft resistance of the pile. QS is calculated using the formula 2.5 into N average into AS. 2.5 is the coefficient for silt, and for sand, the coefficient is 2. Next, we proceed to summing up all the QS values. After that, we calculate the volume of the pile with respect to depth. Multiply that value with the unit weight to get the weight of the pile. After that, we calculate the uplift capacity. This is calculated as the soil is not compressed. The uplift capacity is half of the skin friction divided by the factor of safety, and then the pile weight plus the pile weight. Next, we have a proposed pile diameter of 1.5 meters and a pile length of 16.5 meters. We only need the SPTN values from 4D below and 10D above, which is 1.5 meters to 22.5 meters. Now we calculate the base resistance. Since we only need the values from 1.5 meters to 22.5, we extract this table from the previous table. The N average is calculated to be 18.7. The base resistance is then calculated by using the formula 300 into N average into AS. 300 is the coefficient for a base resting in silt. Now we obtain the total resistance by adding up the base and shaft resistance. We get that to be 46,279. We perform two methods of obtaining the design value. The first method is to divide the total resistance by a factor of safety of 2.5, and the other method is to first divide the base resistance with an FS of 3 and the shaft resistance with an FS of 1.5. We take the lower value as the design value, which is 18,512. Then it is multiplied with 4 to get the combined resistance of 4 piles. We check the values against the loads imposed on the structure, and it turns out to be well under the design resistance, so we can say that the design is okay. Now we calculate for the eccentricity, as there is a horizontal load acting on the structure. The moment in the YY direction is 1040 kilonewton meters, and the eccentricity is 0.104. We use the QN formula to calculate the applied load on all 4 piles. Since the allowable capacity is 18,512, the design of the pile is okay since each pile is able to carry the applied load.
So the last one, conclusion. In our design, pH5 is more critical. So that's why it's backed for allies in our foundation design. Retaining wall is planned as an ultimate to support the bridge framework. After finishing the suitability testing, it was discovered that FS overthinking equal to 3.73 larger than 2.5. For follow foundation, eccentricity at B direction is determined with a value of 0.49. The ultimate bridge capacity and net allowable bridge capacity determined by the allies are 1,747 and 1,598 kilonewton meter square. For individual pile, the value of allowable pile capacity Q all optimate in a single pile, which is 15,341 kilonewton. So and in our pile foundation with four piles at 16.5 depth can a vertical load of 10,000 kilonewton and transfer allowed 800 kilonewton on a pile cap. Thank you so much.